Welcome to The Explainer. Today, we're going to tackle something huge, something that literally makes all life on our planet possible. We're talking about Earth's energy budget, this incredible, delicate balancing act that's happening all around us all the time.
I mean, have you ever really stopped to think about it? Why isn't our planet a frozen wasteland like Mars, or a scorching hothouse like Venus? We're just floating out here in the vastness of space. So what is it that keeps us in that perfect sweet spot for life?
Well, the whole secret lies in something called the Earth's heat budget. And honestly, the best way to think about it is like a bank account, but for energy. You've got energy coming in from the sun. Those are your deposits. And you've got energy radiating back out into space. Those are your withdrawals. For the planet's temperature to stay stable, the books have to balance. What comes in must go out. And it's that balance that makes our world what it is.
Okay, so to really get our heads around this, let's do a little thought experiment. We're going to follow the journey of 100 units of sunshine. Just a nice round number to make it all easy to track. Let's see where it all goes.
All right, here we go. Picture this, 100 units of pure energy from the sun. That's our starting point, 100%, hitting the very top layer of our atmosphere. The journey begins right here.
So right off the bat, something really interesting happens. A pretty big chunk of that energy, about 30 of our 100 units, doesn't even make it in the door. It gets bounced right back out into space by things like bright white clouds or shiny ice caps. It's like a cosmic mirror. So boom, 30 units are gone before they can do a thing.
Okay, so that leaves us with 70 units that actually get into the system. Now, where do they go? Well, the atmosphere grabs a piece of the action, soaking up about 20 of those units, but the lion's share, the big 50 units, makes it all the way down to the surface, warming up the land and the oceans. This is the direct heat you feel from the sun.
So, 50 units. That's what the surface gets directly from the sun. But does that sound like enough to you? To keep the entire planet at a comfy average temperature? You'd be right to be skeptical, because it's not even close. There's another, much bigger source of heat for the surface, and this is where things get really cool.
And that bigger player? It's the atmosphere itself. It's not just about absorbing a little sunlight on the way in. No, its real job is what it does with the heat coming off the Earth's surface. It acts like a giant cozy blanket, trapping heat and then radiating a bunch of it right back down.
And just look at this number. This is wild. On top of the 50 units from the sun, the surface gets hit with an extra 94 units from the atmosphere. Let that sink in for a second. The surface gets almost twice as much energy from our own atmosphere as it does directly from the sun. That's the greenhouse effect in action. It's what keeps our planet from being a frozen rock.
Okay, let's do the math. The surface is getting 50 units from the sun, plus 94 from the atmosphere. That's a whole lot of energy. But remember, the budget has to balance. To avoid heating up forever, the surface needs to get rid of all that energy. It has to send it back up. So how does it do that?
Well, it has a few trucks up its sleeve. A big chunk just radiates away as heat. Then you've got about 7 units that hitch a ride upwards on thermals of warm air. That's convection. But then there's the real workhorse. A massive 23 units get moved by one of the most powerful cooling processes on the planet, evaporation.
This energy moved by evaporation has a cool name, latent heat. Latent means hidden, and that's exactly what it is. Think about when you get out of a pool and you feel cold. That's because evaporating water is literally pulling heat energy out of your skin. That's latent heat. The oceans do the same thing, sending huge amounts of this hidden energy up into the atmosphere. It only gets released as actual heat later on, when that vapor condenses to form a cloud.
So if you add it all up, the planet as a whole is in perfect balance. 100 units in, 100 units out. The books are balanced, but not so fast, because here's the twist. That beautiful balance is just a global average. If you actually look at different parts of the planet, things are wildly out of whack.
And this is a perfect way to see it. The tropics, around the equator, get blasted with direct sunlight all year. They're taking in way more energy than they're giving off. They have a massive energy surplus. But now look at the poles. They're constantly radiating heat out to space and getting much less in return. They're running a deep energy deficit.
So this creates a pretty big paradox, right? If the tropics are constantly piling up heat, and the poles are constantly losing it, why isn't the equator a boiling inferno and the poles frozen solid beyond imagination? Logically, that's what should happen. But it doesn't. So, what gives?
The answer is just awe-inspiring. Our planet has its own built-in, global-scale heating and air conditioning system. It's like a giant thermal engine that's always running, and its one job is to move all that extra heat from where there's too much to where there's not enough. And how does this engine work? Well, it's powered by two massive forces, the winds in our atmosphere and the currents in our oceans. These are the great equalizers.
Just picture a giant planetary conveyor belt. The winds and oceans scoop up all that extra heat from the tropics, and they physically carry it towards the poles, warming them up. This constant circulation, this massive redistribution of energy is everything. It's what stops the extremes. It's what makes the vast majority of our planet livable.
And you know what? This isn't just some abstract climate science. This process is the reason you have weather. Literally, that endless movement of heat from the equator to the poles is what powers our weather systems. Every storm, every front, every windy day, it's all part of this giant planetary balancing act.
So when you put it all together, the incoming sun, the reflection, the greenhouse blanket, the winds, the oceans, you get this beautifully intricate system that has kept our planet's climate remarkably stable for a very, very long time. The budget has always balanced itself out. Which, of course, leads us to the big looming question of our time. What happens when we start messing with the numbers? What happens when we start to tip those very delicate scales?